Okay, for the last video in this lesson, we're going to talk about paper cutting. And I want to demonstrate something for you. So we're going to fill in this chart as we go. And I have right now an entire piece of paper. Whole piece of paper, 8.5 by 11. And what we're going to do is cut it in half. And I'm going to keep one piece in my hand and I'm going to lay one half on the desk. So here we go. Then we're going to fill in the chart as we go. This brings us up to speed with what we have so far in the chart. We just made one cut. Half of it is in my hand. How much of it is on the desk? Oh, that would be 1/2. And the total amount on the desk, now I'm not counting my notes, I'm just counting this little guy right here, laying on this little green piece right here. That would be a half a piece of paper. Okay, we're going to make our second cut. When we make our second cut, there we go. We'll piece them together like we're trying to put them back together. Amount in my hand. How much of a piece of paper do I have right now in my hand? Give me a fraction. What is it? I believe that would be 1/4. I hope you said that. Okay. How much did I just lay on the desk? Same amount. It's 1/4. How much do I have on the desk total? Again, not counting my notes. Not counting the notes, just counting these pieces. How much of a piece of paper is this? Well, if I was to split this into fourths, then I have 3/4. So it is a half plus a fourth, and last time I checked, of course, that was 3/4. Okay, if you can't see that, I know I've zoomed it way out so we can do the other, but that says 3/4 right there. All right, let's keep going. We're going to cut it in half again. The fractions are going to start getting a little messier, but that's okay. This was cut number 3. And by the way, we know this pattern. That's going to be a 4 and that's going to be a 5. You can go ahead and fill that in if you want to. So how much do I have in my hand right now? How much of an entire piece of paper is in my hand? Well, it's, you can kind of tell by the way they're laying, it's half of a fourth. Half of a fourth is 1/8. I just laid 1/8 on the desk, and so now we have what I just had, 3/4 plus 1/8 is going to give us 7/8. So in case you can't see that, again, that says 7/8. Let's keep going. We'll speed this up a bit because you're starting to notice the pattern, I hope. So let's slice this in half. There we go. How much did I just lay on the desk? Equal to what I have in my hand right now. How much of a piece of paper are each of these? Well, it's half of an eighth. That is 1/16. Obviously, that is 1/16. You know the pattern. These two columns are going to be the same. We're going to add what we already had on the desk, the 7/8, with the 1/16. 7/8 plus 1/16. Double this numerator to make that denominator doubled as well. That's going to give us 15/16. Boy, there's some fantastic patterns that are happening here. All right, we chop that in half. How much is in my hand? Half of a 16th. Half of a 16th is a 32th, a 32nd. Same here, 1/32. 15/16 is what I had. I just added a 32nd to that. Adding 1/32 to it gives me 31 32nds. Okay, so let's just follow this logically. If I was, and we're reading this question right here, if I was somehow able to do this an infinite number of times, how much of the piece of paper would be on the desk? Okay, well if I was to keep doing this, and I can just keep cutting it in half and cutting it in half and cutting it in half. We'll slide this around so you can see it. It's going to make the paper kind of crooked, but you'll be okay. And we're going to keep cutting it in half and cutting it in half. And you know, you can piece this together if you really want to. We're going to keep cutting it in half and cutting it in half and then cutting it in half. And I can do this until I just simply can't cut anymore. How much of the paper, of the original paper, will be laying on the desk? Hopefully right now you're saying the obvious. Hopefully right now you're saying the whole sheet, Mr. Reader. Yeah, and there comes a point where you can't cut too much anymore. Oh yes you can. Oh yes you can. And you can keep cutting it and cutting it and cutting it. And then you're going to reach a point where you're about to split a molecule, and that starts an atomic reaction, so let's not go there. But you can just keep cutting it smaller and smaller, and if you were to do that forever and ever and ever, oh, no, never mind. Fingernail clippers aren't cooperating. There we go. See, this is getting difficult, isn't it? And we're going to keep cutting that in half. How much of the piece of paper is on the desk? A whole piece, minus that right there. So the answer to this question right here, and I'm going to cut this piece one more time just because I'm going to see if I can. The whole piece is there other than that. So if I could do this to infinity, as if I could, how much of the piece of paper would be on my desk? One whole piece. So let me write that down, then we'll try to cut this again. One whole piece. You know what you just did? Whether you realized it or not? You just figured out an infinite sum, an infinite geometric sum. See it? It's right there on the edge. Okay, you may not be able to see it, but it's right there beside the callus on the end of my finger. I don't think I can cut that in half anymore. You know what? I'm going to give it one more shot. If I start bleeding here on the video, it's going to be kind of awkward. I don't think I can. I don't think I can do it. Can't do it. All right. Now I'm going to have this paper all over my floor in my house. Anyway, we just had one whole piece. So we just found an infinite sum. We added and added and added and added and added and added. But eventually we realized that it's going to approach something and there's no need for us to keep adding it anymore. I mean, let's be practical. We can do this forever and ever and ever trying to chop it in half, but you saw it yourself just a second ago. Pretty much the entire piece of paper was laying right there. You saw it. The whole piece of paper was pretty much there. And it's the same as what we did here. It's pretty much a half. It's a half. You know, you can round that up. It's obviously clearly 0.5. So an infinite sum is going to tend to go towards a certain number. So when it says evaluate these infinite sums, well, how many numbers am I adding? I'm adding all of them. I'm adding an infinite number of things. And so there is a formula for an infinite sum. It is on your formula sheet and it is S. It does not have an N. It does not have an N because we're not adding a specific number of things. N is how many things we're adding, and we're not adding a specific number, we're adding all of them. And here it is. A1 and then 1 minus R. Okay, and here's the easy part. This is a pretty easy formula. A1 is 1250. I don't know where I was going with that. And then R, well, we don't know what R is. We grab a calculator. Shoot, let's not grab a calculator. I'm not going to grab a calculator. I know what happens. It's geometric, clearly. 250 divided by 1250, that's 1/5. 1 minus 1/5. Let's put that in parentheses. Doesn't hurt, it helps. Alright, so here goes. 1250 divided by 1 minus 1/5. Make that 0.2 if you like, and there we go. If we were to add this plus this plus this plus a fifth of it plus a fifth of it plus a fifth of it, and we could hit enter on our calculator and add these over and over and keep going forever and ever and ever, it would eventually get to a point where it would round off to that. Can I prove a point to you real quick? I'm going to try to keep it quick. 1250 plus 1/5 of our last answer, plus a fifth of our last answer, plus a fifth of our last answer, plus a fifth of our last answer, and you know what? I just messed this thing up. I think I did. I was trying to prove a point, so if you're following along with me, let's try it again. Plus, let's do 0.2. $12.50. There we go. So 1,500. And then we're going to add that to a... Shoot, I done messed up. Okay. Yeah, I was going somewhere with this, and I thought about editing this part of the video out, but clearly I was not typing in my calculator right. Let me take this opportunity just to clarify what I was doing wrong. I was adding together this with that, and then I was going to add 50 to both of those, and the next one to all of those, and the next one to all of those. And in the process of doing so, I kept adding the first ones over and over. Sorry. It's my lunchtime and I'm about to eat lunch, so I'm hungry and I'm not thinking straight. What I was trying to prove was if I could do this in my calculator, it would end up being that. Teachers make mistakes too. I'm not going to edit this out. Let's just go with it. Long story short, adding these numbers, if I was to keep listing them, it would round to that. Sorry I wasted a minute and a half of your life with that. Please forgive me. All right, R is... Oh my gosh, what is R? Well, first of all, we know that it's geometric because you're not adding the same thing or subtracting the same thing every time. Also, we know that it is infinite because it keeps going forever because it doesn't have an ending number. So it's negative 40 over 80. Here we go. Negative 40 divided by 80 is negative 1/2. We're multiplying by negative 1/2 every time. So we're going to add together this infinite sum. So S equals the first one minus 1 minus negative 1/2. Be careful with your signs in the denominator there. Don't make calculator mistakes like I just did. Sorry about that. There we go. 53.3, repeating. 53 and a third. 53 and a third. There we go. Okay, the next one. What's R? R is, well, we're doubling. We double. Oh, so it's 2. It's 2 divided by 1, which is 2. Is this finite or infinite? This is infinite. This is infinite. Okay, and I would like to write the formula, but I'm not going to. I'm not going to. And here's the reason I'm not. Let's do it in the calculator. Let's go back to this one. I'm going to try to do this one right. 80 plus negative half of 80 plus negative half of negative 40 plus negative half of that plus then plus negative half of that plus negative half of that, and already I'm getting towards a number that's pretty close to this. Okay, let's do this one. 1 plus 2 plus 4 plus 8 plus 16. Okay, what's the next number? 32, 64, 128, 256, 512, 1024, 2048. We'll stop there. We get a big number. It's not tending to go towards any particular number. If I was to add these, it starts really looking like that. If I was to add these, because, and here's the kicker right here, this is the whole point of what I'm trying to say. Because these numbers are increasing, I cannot find this infinite sum. If I added 1 plus 2 plus 4 plus 8 plus 16, I would get infinity. There are mathematicians that could probably disagree with me on that. There's some really crazy things that happens when you add together numbers like this going towards infinity. But long story short, it tends toward infinity. So adding these numbers, S equals what? Cannot find an infinite sum. But Mr. Reader, it's geometric. Why can't you find it? Oh, I don't know. Let's find out. When can I use the formula for an infinite sum and when can I not use it? Well, it worked here and it worked here. But if I was to try it here, I'd get a crazy answer. I'd get something and it wouldn't work. And I'll tell you why it wouldn't work, because these numbers are increasing without bound. So, and the way we write it is the limit as n approaches infinity, and I'll kind of show you what that looks like later on in class. But as n approaches infinity, as we get bigger and bigger, then we're not going to be able to find an infinite sum because these numbers are increasing. These numbers are getting closer to 0. These numbers are getting closer to 0. Now these are bouncing back and forth between positive and negative, but let's ignore the signs for a minute. 80, 40, 20, 10, 5, 2.5, 1.25, and then 0.625, and it's going to get smaller and closer and closer and closer to 0. This is going to go down as well. I want to prove a point here. I really do, and I'm going to do this one right. Let's graph this one real quick. You don't have to type a thing, but I'm going to type it in. 1250, 250, 50, and then whatever 50, a fifth of 50 is, and then a fifth of that is. And then if I was to graph it on my calculator, it looks like that. Notice that it is decreasing. It is getting closer to the x-axis, but if I was to graph that one, and I will super fast, if I was to graph that one, it's going out, away. And so I can't add that because it's going without bound. Okay, so to answer this next question, we'll sum this up real quick. Pardon the pun, sum this up real quick. When can you use the formula for infinite sum and when can you not use it? When, there's more than one answer here, the numbers in the series, notice I didn't say sequence, series is when we're adding them. I'm going to use one of the words down here, diverge from 0. Let's throw one other thing in here, or are constant. We cannot find an infinite sum. There we go. Spell it right. I am getting hungry. Can't even write. Cannot find an infinite sum. We can't do it because these numbers are increasing. So when I add those together, what I'll get? Well, it pretty much goes towards infinity. Okay, a converging sum, also known as convergent. You'll see that word sum. And by the way, diverging sum is also known as divergent, not to be confused with the movie that no one really watched. A converging sum basically gets closer to 0. The numbers themselves and the terms get closer to 0. So the terms approach 0. Let's kind of block this off so they don't run together. And another way of looking at it is the R value. Notice what R was here. Notice what R was here. It was a fraction that is less than 1. Between 0 and 1, that one actually is between 0 and -1. But R needs to be, I'm going to write it mathematically, needs to be between 1 and -1. If R is between 1 and -1, then it'll work. A divergent sum, a divergent, not divergent, just pronouncing things. This is where the terms, and this is pretty much what we said right here, but we'll make it a little more concise. The terms go away, poorly worded, but we'll go with it, from 0, or remain constant. Like if I had a sequence that was 5, 5, 5, 5, 5, 5, well, when you add those together, what do you get? A whole bunch of 5s, and it tends towards infinity. The terms go away from 0 or remain constant. Another way of saying this is that R is greater than or equal to 1, or R is less than or equal to -1. Okay, there we go. And that's how you test for convergence or divergence.